Okay, so now you guys are sort of experts at identifying aromatic, anti-aromatic, and non-aromatic compounds. We're going to expand on that a little bit. Of course, there are other aromatic compounds that are, basically just larger versions of benzene. These are called anilines. And so here are just some examples here. Notice that it has 6, 10, 14 pairs of electrons. Those meet those Huckel rules. This is just how many electrons they have in that conjugated ring network. So these would all be considered aromatic. It actually, if you had a bond, whether or not there was a sigma bond between those carbons is irrelevant. It's still aromatic. These are some nice examples of aromatic compounds. Notice that they also have their own fancy names. Don't worry, I'm not going to make you memorize those. Okay, bottom line is you can have larger compounds that are still aromatic as long as they meet those two criteria that we laid out 2 lectures ago. Another thing that we talked, and then we have our diagrams that illustrate that. So another thing that we talked about already is when you have ionic molecules, right? Molecules that have a net charge. And so for this molecule, we said that this is also aromatic. This is just drawing all the resonance structures. But let's convince ourselves that this is indeed aromatic. Remember, what was that first rule? Has to have that line of sp2 hybridized carbons. So these guys are certainly sp2 hybridized. And then we get to that carbocation. We know that carbocations are sp2 hybridized and they have that empty p orbital, right? And then we can go through and make sure we follow Huckel's rule, have the correct number of electrons. This has 2, 4, 6. And so that indeed does follow Huckel's rule. This is aromatic, right? There's no electrons contributed from this atom because it's got that empty p orbital. So then we already sort of saw these examples, right? This idea of a charged molecule being able to be aromatic as well, okay? So then let's take a look at these 2 examples, right? So for this particular one, again, sp2 hybridized carbons, and then it's a carbocation. So this has your network, it meets rule 1 correctly, but what it fails at is it only has 2, 4, and so it is anti-aromatic. Okay, and then if we go over here, well, if instead of having an empty p orbital, it had a full p orbital, a pair of electrons, that would make it so it's aromatic. Okay. There's something a little counterintuitive, or not counterintuitive, but that goes against stuff that we've learned previously about that. Is that means that this carbon here, if this is going to be aromatic, remember that first rule, it means that all of these carbons are sp2 hybridized as well as this one, okay? Which means that this pair of electrons, so if this is sp2 hybridized, this pair of electrons right here has to live in a p orbital, right? That's the only way that it can delocalize around this ring, create that network of conjugation, is if that pair of electrons is sitting in a p orbital, okay? Meaning that that carbon's sp2 hybridized. So why does that go against what we've learned thus far? Well, let's take an example of, a simple example of ammonia. When we were figuring out the hybridization of this nitrogen, we said that it was sp3 hybridized, meaning that this pair of electrons is sitting in an sp3 hybrid orbital. Usually, pairs of electrons we count as molecular or electron regions. They usually live in hybridized orbitals. In this particular example, though, it has to be living in a p orbital in order to contribute to that aromaticity. And that's why it does that, right? So instead of, if this carbon was sp3 hybridized, we wouldn't have an aromatic molecule, right? So instead, it's going to put the pair of electrons in a p orbital, making it sp2 hybridized. That way it can be an aromatic molecule, right? So then that pair of electrons can delocalize around that ring. Okay, so in this case, either of these charges will lead to an sp2 hybridized molecule. This one, we always said carbocations were. Now we're learning that those anions will, in order to be able to participate with the conjugation of the ring. Okay, and you can see this is sort of illustrated in the acidity of this cyclopentadiene compound, right? Or its willingness to give up a proton. Remember, like, if you had just a random alkane, these hydrogens have a pKa of like 60, meaning that they're basically impossible to remove. Cyclopentadiene, though, has a pKa of 16, which means that it can be removed by just hydroxide, which isn't a crazy strong base. I mean, it's a strong base, don't get me wrong, but you don't have to use something insane in order to pluck that electron off. The reason is because when you pluck that, proton, because when you do, that pair of electrons gets donated to that carbon, and now this is aromatic. So it forms a nice stable anion. Okay, so again, just using the property of pKa to illustrate that, you know, you create this nice stable aromatic compound. Okay, so we sort of had already talked about the charged molecules, the cations and anions, and hopefully that all makes sense. Now we're going to go on to heterocyclic atoms and show whether or not they are going to be aromatic. Okay, so let's take a look at two examples here. First, heterocyclic. Well, first thing that's important to remember, right, is that nitrogen likes to have 3 bonds and 1 lone pair. So each of these compounds has a lone pair of electrons on that nitrogen. So let's take a look at pyridine, which is very similar to benzene, except for there's nitrogen in that ring instead of it all being carbons. Nonetheless, you still have everything is sp2 hybridized, including that nitrogen, and you have 2, 4, 6 pairs of electrons meeting Huckel's rule. Not pairs of electrons meeting Huckel's rule. Okay, so if you looked at the sort of molecular orbital diagram picture of it, you see that you have all those pi bonds sitting next to each other. That leads to that conjugated ring. That means that this pair of electrons in that lone pair isn't part of that conjugation, right? Nitrogen already has a pi bond. That's what's participating in the conjugated ring. That pair of electrons is not, so it's going to be sticking out to the side in an sp2 hybridized orbital, not living in a p orbital. So now let's go on to pyrrole. And we'll see that this, well, we know that these are all sp2 hybridized. This is an example just like ammonia, where just by doing the counting rules that we learned, you know, in general chemistry or at the very beginning of the first semester, we might expect this to be sp3 hybridized. But that would make this compound non-aromatic. Whereas if instead nitrogen was sp2 hybridized, then it could keep this pair of electrons in a p orbital and thus allow it to be aromatic, right? Because then that would give me my 2, 4, 6 that I need to meet Huckel's rule. So pyrrole is aromatic because it puts that pair of electrons, that lone pair, in a p orbital. So actually, let me be clear, because my coloring scheme, I use blue to indicate the sp2. The actual pair of electrons itself lives in a p orbital. Okay, so again, if we want to look at the molecular orbital picture, pictured way better than me, now we see that the nitrogen is sp2 hybridized, and in particular, that lone pair lives in a p orbital, so that you have that conjugated network and it can be aromatic. Okay, so the take-home message here is that atoms will change their hybridization in order to have electrons that can participate in conjugation. Okay, that's going to be your challenge for this lecture, is figuring out whether or not a pair of electrons is in a p orbital, what the hybridization of that atom is. I think I just copied that page on accident. And again, these properties are going to be illustrated in the basicity of these compounds, right? So in this case, their willingness to accept a proton and get a positive charge. Well, pyrene, or rather pyridine, is a pretty good base, right? And that's because when it does accept a proton, it's still aromatic. It hasn't messed anything up. Pyrrole, on the other hand, is a really crappy base, and that's because if it accepts a pair of electrons, then the hydrogen has to be sp3 hybridized, making it non-aromatic, right? So we can look at remember, we can look at the pKa's of the conjugate acid to get a sense of basicity. If its conjugate acid is really strong acid, that means that this is a crappy base. Okay, so again, just using pKa to illustrate this phenomenon. And just like we said that an atom can sort of change its hybridization in order to meet the criteria for aromaticity, the sort of opposite is going to be true. So what do I mean by that? Well, we already said that this nitrogen is sp2 hybridized, so we can have that ring, and that this pair of electrons here is going to live in a p orbital. Again, just sort of more nicely illustrated down here. And it does that specifically so that it can be aromatic. Well, let's take a look at this compound here. Okay, very similar, right? Nitrogen also has a lone pair. The question is that lone pair in a p orbital so that it can contribute to the network, right? To the conjugated pi bonds, because I have this network of sp2 hybridized atoms here. Let's just say that it was. Let's say that nitrogen was sp2 hybridized. And just like in our pyridine example, this pair of electrons lived in a p orbital. Well, then that would mean that I have 2, 4, 6, 8 electrons in this network. That would make this compound anti-aromatic. Remember, anti-aromatic is bad. It's high energy. Compounds don't want to be anti-aromatic. So in order to avoid that, this will not hybridize in an sp2 fashion. It will remain sp3 hybridized, specifically so that instead of being anti-aromatic, this compound would be considered non-aromatic, right? So just like a lone pair, if necessary for aromaticity, will put itself into a p orbital. If putting it in a p orbital would make it anti-aromatic, it's not going to do it. It's going to remain sp3 hybridized so that it can be non-aromatic, right? Anti-aromatic's bad, non-aromatic is better.